The bit. This is the smallest possible unit of digital information. Think of it as a single yes or no answer, a 1 or a 0, an on or off switch. Every piece of digital data, whether it's a text message or a 4K movie, breaks down into millions or billions of these tiny bits. A bit can only hold one of two values, which makes it incredibly simple but also incredibly limited on its own. But here's where things get interesting. 8 bits combine to form something much more useful called a byte. This is where digital storage actually becomes practical. A single byte can represent one character of text, like the letter A, the number 5, or a punctuation mark. When you type your name, each letter takes up exactly 1 byte of storage space. It's the fundamental unit that makes readable information possible in the digital world. The beauty of bytes lies in their simplicity. They're large enough to store meaningful information, but small enough to be incredibly efficient. Every email you send, every document you create, and every password you type starts with bytes working together. Even though a single byte seems insignificant, it's the building block that makes all digital communication possible. Moving up from individual bytes, we encounter the first major milestone in digital storage: the kilobyte. 1 kilobyte equals exactly 1,024 bytes, not 1,000 as you might expect. This happens because computers operate on binary systems, where everything multiplies by powers of 2 rather than 10. So, while it might seem logical to use 1,000, the actual measurement is 1,024. A kilobyte can hold roughly half a page of typed text or a very basic black and white image. In the early days of personal computing, entire programs were designed to fit within just a few kilobytes. The original floppy disks, those square plastic things your parents might remember, could store around 360 kilobytes total. That was enough space for basic word processing, simple games, and essential business software. To put this in perspective, a single text message on your phone uses less than 1 kilobyte. The entire text of a short email fits comfortably within a few kilobytes. It shows just how far technology has advanced when you realize that what once required careful planning and optimization now happens without us even thinking about it. The next level brings us to megabytes, where digital storage starts feeling more familiar to modern users. 1 megabyte equals 1,024 kilobytes, or roughly 1 million bytes. This is where we begin seeing measurements that relate to everyday digital activities. A typical photo from your smartphone camera takes up between 1 and 2 megabytes, depending on the quality settings and what's in the picture. Music files also live comfortably in the megabyte range. A 3-minute song in MP3 format usually requires about 3 to 5 megabytes of storage space. Back in the 1990s, owning a computer with 500 megabytes of total storage felt like having unlimited space. You could store thousands of documents, hundreds of photos, or dozens of songs without worrying about running out of room. The megabyte era represented a turning point in personal computing. For the first time, average users could store meaningful amounts of multimedia content. Photo albums became digital, music collections moved from physical CDs to computer hard drives, and software became more sophisticated because developers had more storage space to work with. Next comes the gigabyte, which equals 1,024 megabytes, or approximately 1 billion bytes. This is where modern digital life really begins. A single gigabyte can store around 600 photos, 230 songs, or one 2-hour high-definition movie. Most smartphone apps measure themselves in hundreds of megabytes or single-digit gigabytes, while operating systems like Windows or Mac OS require several gigabytes just for basic installation. Gaming consoles, laptops, and desktop computers now come standard with storage measured in hundreds of gigabytes or multiple terabytes. What seemed impossible just 20 years ago is now considered entry-level. The shift to gigabyte thinking changed how we interact with technology. Instead of carefully managing every file, we started thinking about bulk storage, keeping entire photo libraries, music collections, and video libraries readily available. The progression continues with terabytes, representing 1,024 gigabytes or 1 trillion bytes. A single terabyte can hold approximately 250,000 songs, 500 hours of high-definition video, or several million documents. External hard drives, gaming consoles, and high-end laptops now commonly feature 1 or 2 terabytes as standard equipment. Cloud storage services offer terabyte packages for backing up photos, documents, and other files. What makes terabytes significant is that they represent the first storage unit where individual users can realistically store everything they create or consume. Every photo you've ever taken, every song you've ever enjoyed, and every document you've ever written can fit comfortably within a few terabytes. This is also where professional and enterprise storage begins. Video editors working with 4K footage, Photographers managing raw image files and businesses maintaining customer databases start thinking in terabytes. It's the bridge between personal storage needs and professional data management. Beyond terabytes, we enter territory that most individuals never directly encounter, but that powers the digital world around us. These larger units represent the scale at which major technology companies, research institutions, and internet infrastructure operate. Understanding these measurements helps explain how services like streaming video, cloud storage, and social media platforms manage to serve billions of users simultaneously. The jump from personal storage to enterprise storage represents one of the most dramatic increases in computing history. While your personal devices measure storage in gigabytes and terabytes, the systems that deliver content to your devices operate at scales that are difficult to comprehend. Petabytes represent the next massive leap in storage capacity. 1 petabyte equals 1,024 terabytes, or 1 quadrillion bytes. To grasp this scale, a single petabyte could store 13 years of continuous high-definition video content. That's enough space to record every waking moment of your life in crystal clear quality for over a decade. Companies like Netflix manage petabytes of video content to stream movies and shows to millions of users simultaneously. Research facilities such as CERN, the European Physics Laboratory, generate and store petabytes of data from particle collision experiments. A single petabyte could hold 500 billion pages of text, which is more written content than most people could read in several lifetimes. Weather prediction services, satellite imaging companies, and medical research institutions routinely work with petabyte-scale datasets. When scientists map the human genome, track climate patterns, or analyze astronomical observations, they're dealing with petabytes of raw information that must be processed, analyzed, and stored for future reference. The infrastructure required to handle petabytes is staggering. Specialized data centers with hundreds of servers running continuously are necessary just to keep this amount of data accessible and protected. Backup systems, redundancy protocols, and cooling systems become critical components when managing storage at this scale. Moving beyond petabytes brings us to exabytes, which equal 1,024 petabytes, or 1 billion gigabytes. This measurement enters the realm of global internet infrastructure. Back in 2001, researchers estimated the entire internet contained roughly 5 exabytes of total data. Today, humanity creates more than that amount every single month through social media posts, video uploads, online transactions, and digital communications. 1 exabyte represents approximately 1 trillion books worth of text, or around 250 million DVD movies. The scale becomes almost incomprehensible when you consider that storing 1 exabyte would require an entire warehouse filled with servers, backup systems, and cooling infrastructure operating around the clock. Major technology companies like Google, Amazon, and Microsoft manage exabyte-scale storage systems to power their cloud services, search engines, and online platforms. Every search query, every video stream, and every file upload contributes to the massive flow of data that these systems must handle continuously. Exabytes also represent the scale at which artificial intelligence and machine learning systems operate. Training advanced AI models requires processing enormous datasets that often measure in exabytes. The computational power and storage capacity needed to develop modern AI systems pushes the boundaries of what's technically possible. The next level introduces zettabytes, representing 1,024 exabytes, or 1 trillion gigabytes. Global internet traffic in recent years has reached approximately 4 zettabytes annually. That encompasses every video streamed on YouTube, every photo shared on social media, every email sent, and every file downloaded across the entire planet. A single zettabyte could store 30 billion 4K movies, which represents more entertainment content than anyone could consume in multiple lifetimes. When technology executives and government officials discuss digital infrastructure, cybersecurity, or data privacy policies, they're often thinking about zettabyte-scale information flows. This is where data storage stops feeling human-sized and starts operating at planetary scales. The economic, environmental, and technological implications of managing zettabytes of information affect global energy consumption, international data policies, and the fundamental structure of how modern society operates. Cloud service providers, telecommunications companies, and internet backbone infrastructure must coordinate to handle zettabyte-scale data flows efficiently. The cables, satellites, and data centers that enable global internet connectivity are designed to manage these enormous volumes of information seamlessly. At the absolute top of officially recognized storage units sits the yottabyte, equal to 1,024 zettabytes or 1 septillion bytes. This represents the largest standardized measurement for digital storage, so massive that no current system can actually store or process a full yottabyte of information. A single yottabyte could theoretically hold every document, photograph, song, video, and piece of digital content ever created in human history, with vast amounts of space remaining unused. Scientists and technology researchers use yottabytes as a theoretical framework for imagining future data growth and storage requirements. Current projections suggest that if global data creation continues accelerating at its present rate, humanity might eventually need yottabyte-scale storage systems within the next several decades. This would require technological breakthroughs in storage density, energy efficiency, and data management that don't exist today. The concept of yottabyte storage challenges our fundamental understanding of information management. The physical infrastructure, energy requirements, and technological complexity needed to create and maintain yottabyte systems would represent one of the largest engineering projects in human history. Subscribe if this helped you understand the invisible infrastructure that makes our digital lives possible.